Okay, so what is a smart market, right? So a smart market is a system that's contrary to a rule-based system. A rule-based system is something that we need to know ahead of time how we want it to react down to the fine detail. And if you take something simple like a GPU marketplace, that would involve looking at the demand, looking at the actual utilization of the GPUs that you have, the queues that are building up, wait times, pricing. There's a lot of different sensor data which would be required to make a decision based on that, even in a simplified market. So a smart market is this idea that rather than knowing the logic up front, you basically subject a genetic algorithm to the data or the simulation, and it would then learn the best potential weightings to use to resolve network congestion or whatever the objective happens to be. Just to kind of key back up with the slides, so dynamic adaptation, the market will adapt to the conditions that the market is actually experiencing with, whether that's surges or actually shocks where no traffic's coming in. So objective driven behavior, replace the rules with programs that are based on the UTMM, which is the concept in the paper. This kind of combination of genetic algorithms and the actual market, or at least some kind of simulation where they operate in, and that would be the kind of definition there. Self-regulating. We're obviously talking about GPUs now, but the idea here was to prove out the basic premise on something slightly simplified but still pretty complicated, and allow us to then be able to implement that in a blockchain setting. So stuff like that. So there's a lot of different areas that it could be applied to. And obviously, from what I'm saying here, a lot of people might recognize that this sounds very similar to other forms of deep learning and neural networks. And in many ways, it is similar. Like, we're looking at things that are an inflection through. So instead of something following a set of rules and patterns, you've almost got a polarizing direction, or a set of weights. Something comes through it and comes out the other side transformed, and that's effectively it. So it's a function, a function. The price in many ways has a heavy influence over market demand. So if Bitcoin or some other utility, right, was to suddenly go 100x overnight, you would notice a real decline in the actual throughput of the utility, because you've priced out people in the market, right? And people go cold as soon as something becomes cost prohibitively expensive. So it's a nice first lever to have here. So if you imagine, well, I mean, I guess, and I'm talking in the slides like what we're actually solving, right? I mean, there's no point in me necessarily talking through these just yet then, but what we're saying is that a rule-based system versus a system that that is effectively going to act as this function would need only one lever, right? So the lever being price. Price affects all the other things. So demand, the actual time to process, all of that can be affected by price. So both the rule system and the GA only control price, but the difference being is on one of them you're controlling price by saying if Q goes up, increase price by X, right? And pretty much these simple fixed rules. Whereas with the GA, it's applying what it thinks is the best policy and the best adjustment based on the fact that it's had generational training, which has allowed it to kind of condense down the weights to something that achieves a high score consistently. Those are emergent properties under GA. Like that's what I'm getting. That's what I'm getting at. And I have to keep this simple just to keep us on track. But the one lever that we've done here is to prove just in this POC. But effectively, emergent properties are that that you actually find that something as simple as price does affect the market so massively that is the way to kind of get almost for it to learn, if you like. So they started with 2 parameters, end up with 5 parameters at the minute, but there's nothing to stop us from using 100, right? So I guess I'll skip over these ones for now, because I mean, this is mostly stuff that we've chatted about, and it's just kind of trying to frame this as if like I don't know who I'm talking to, rather than just jumping straight into a demo, trying to frame it like what is the concept, why are we proving it out, and then what are the constraints that we've done when we're proving it out. So like I say, price being the only lever in this case, but emergent properties that I'll explain later kind of cropped up within that. So if we just take a basic idea of what a genetic algorithm is, we start with a population, right? Or rather, we would start with a genome, which is one member of a population, right? And within that genome, you have your parameters. And like I said, originally we had two parameters, and that would be the optimal price and the price relative to sensitivity to Q, right? And then I introduced 5 parameters, which were kind of around that, but within the sort of set of being able to check utilization of CPUs, queue length, job length, average wait time, and ultimately like the output price. There's quite a few different parameters in there that can be used. So if we start with 100, for example, right, as the 100 generation, and we pick a system with 5 elites, which is what I've used here. So that's meaning that the 5 top candidates from the first generation get passed into the next generation untouched. There's no parental process, no crossover or mutation, right? But also those 5 sit within the possibility of being selected as parents. So we pick randomly, right, which is part of this. We pick randomly 5 of the population to act as parents, and then we're gonna cross them over and mutate them slightly as well. So add in a bit of randomization. That kind of means that they're not just using the features for one parent and passing them to the other. So when I talk about five features, if we just say features A, B, C, D, and E, then parent A, right, randomly will either keep their own parameter A set, but they'll take parent parent 2's B, right? And it's just a 50-50. That's how that's calculated. So once you have your parents, and I'll show you the formula for calculating it because it's pretty easy. If you have 100, you take 5 elites off, that gives you 95. You need 2 parents for repopulating the 95 again, right? So basically, you're going to need 180 parents to create the children. So when we actually run the training, you'll see this iterative process obviously going on here. But effectively, just to make it sort of clear, generations pass on the elites. There's also parents. Parents repopulate the next generation, and everything's seeded with random values to begin with, and then all policies are tried. So when you talk about a training session, it would be 2 episodes long, so 2 times whatever the number of steps that you've added, right? The iterations or generations. So if we say 100, it's actually doing 200. And that means that it starts with a set of random values, and it's getting the opportunity to try all of the different it's been able to kind of sit in that environment and try 2 different possible ways that it could make that efficient and have its chance for achieving a high score to be able to be passed to the next round and become a parent. So otherwise, it's kind of ensuring that there's a fair chance for a good performer, basically, and we can easily measure performance because it's a reward function. So yeah, so there's 2 ways of solving it. One is to ensure that everybody has the same randomness. So there's 2 things that are going to affect things here. One is there's determinism in the policy, in the sense that if all nodes use the same policy, i.e. this policy wins, everybody's using it on the next round, then that's deterministic because the same data would give the same results. So each node would expect to adjust the price in the same way based on the exact same input. However, the actual generating of the policies isn't deterministic in the sense that there's randomization. So there's randomization within the selection process in the tournaments, but there's also random data injected in the form of sampling for, like you say, the mutations. You could standardize the mutations, and you could technically remove the randomization in part of the tournament selection. So you could make the GA deterministic, but it would need benched against the non-deterministic method. Well, this is the thing I was going to say. The main point for me is
you're actually trying to get nodes to compete to find the best policy. And that is the thing. They don't want that deterministic anyway, because what you want is the same principle that's in the GA itself, which is try all possibilities, and the emergent best ones will pop out. So actually having the GA policy finding should be non-deterministic, but the actual application of the policy is deterministic. So all nodes are like, okay, well, we're all using this V2 policy. So what my price would never just, I would never think that the price should be 10 times what it is. But absolutely, everybody should be searching for the ideal policy. And it's easy-ish to say for certainty to some degree whether that's a successful GA, because it would apply to the back propagated data. So the data that exists, like the historical data, it's always going to produce a higher score. So it doesn't necessarily mean that it's going to be the best in the future, but it's certainly the best based on the data that they have. No, exactly. That's it. As long as, but I think ultimately the output of the end result still would be deterministic in the sense that this policy applied to this set of data will always result in this action. And that's literally because it's hard-coded gradient. Well, it's not a gradient, but it's a weight, but it's the exact same output. So the actual POC components then, right? So we have a simulation environment that simulates a GPU market, right? So people needing GPU compute power, processing jobs that take varying lengths, and use different amount of resources for the length of time that they have the job. Right, a demand generator, which basically will create surges in traffic, or it'll create shocks where the actual supply stops coming in. Right, a reward function, which is basically a calculation based on a YAML file where I would say I want the market to be this fair. I want it to also be biased for price, but I want it to make sure that the congestion never builds up, right? And that there's a thing I've added in called market death, which is basically you can't just push the price up forever, and do you know what I mean? Like just try and salvage the fact that you're overloaded by price, because you'll just kill the market. So an example would be Mhm. Exactly. Um, so the reward function, GA policy trainer, which is basically the training process to actually create the GAs and select the best one for using in the simulation. A rule-based controller, which is a control to show how a simple system can operate when we run the parameters pretty simple, like the demand isn't too high, there's no spikes, it's generally just basic to calculate. If Q too big, put the price up and reduce the demand a bit, right? Like that kind of idea. Or if the queue is non-existent, reduce your price to increase some demand. And then a logger and visualization for it to be able to make some graphs. So just looking at the parameters here, we've got job arrivals, queue time, utilization, price elasticity, and volatility, right? So it shows that we do have a sort of generally lifelike simulation market. If we look at like a few different outputs of that lever pool that we're talking about, so reduced demand would mean that there's fewer arrivals. We can mitigate that by increasing the price. It would lower the system utilization because we're basically increasing the price, and less people are going to want to immediately process jobs, and it would shorten our queues. Decreasing the price will have that similar opposing reaction where we can increase the demand, and then we can increase system utilization and increase the queue pressure. So yeah, basically, I don't think there's any point in me going through all of these, but effectively this would be if I was doing a fresh presentation that was targeted at anybody who hadn't read any of the original material. So we can just kind of jump back into it. But this is the objective YAML that I was talking about before, so it's worth mentioning this. So utilization, we want near 80%, between 80 and 100%, somewhere on the positive side for utilization of the resources. and we want the volatility to be low, and we want fairness in the network to be 20%. So not necessarily all that fair, mostly just trying to generate revenue, which we're having here at 0.4, 40%. Could increase that to 80%, and then the actions that the GA takes will just be ones which are attributable to a high price, right? And it doesn't matter if it tanks the network and all that other stuff. So let me just, more for the selection. This is probably relevant to mention. So this is the parameters and how they're actually working, right? So you've got this Q, which is Q pressure, and this is a target Q. So we want to try and take the Q pressure and the objective, the actual target Q length that we have, and try and find an equilibrium between the two. So that's what the function's actually doing. I would say that's pretty much the next thing. Would say is definitely part of it, because there's no reason why you couldn't apply the GA to that. That would make sense. Mm-hmm. Nice. Right. So this is the dashboard that's running. I'll just stop it just now and then let you see the training. And I've stored some backup weights so that I can run one of the good models versus one of the shit ones. Right. So hold on. That's right. So we'll do a training session here. So let's say we're gonna run for 100 generations. Well, we'll run for 10 generations, and we'll run with a population size of say 20. And we'll run through that. So the best in class on the initial first was 95. So 95 is the total rewards that it managed to get over 400 iterations of the market simulation running. Right. So the basically that was the instantiated random vectors, right? So no very great, right? But then the next one, 103, 99, 20, you can see that the actual trend is moving up. And this average here is the average of the entire population. So this is actually more relevant than the best, because you'll always get outliers who do amazing. But actually, when you start seeing your averages of your entire population coming up, that's kind of when you know your training is working, because that's your parents and the sum of the mutations. So we have 145, right? Like, that's not particularly amazing, but if we say we adjust something like a higher population number to start with, a higher number of potential candidates, we'll see what we get on this, and then I'll run the simulation. I'll run it with a randomized set as well, where I just give it 0 generations. So the previous step, right? It's just like a tick in a market. So it says, I know what the current pricing data is from the last iteration, and it knows the different parameters that we are capturing for network congestion, the general parameters that we're capturing, right? And then it would then run this function over that data and try and assign the price up or down. So it's either going to say we increase the price or we'll reduce the price. And it'll do that at every single step. So it's always taken the previous step to make that decision. The algorithm is trained at training time, and at runtime the policy is fixed. So it's using the same policy, but it's the learned policy. So it's the policy that it learned through the iterations of training, which is really just the GA running in the environment and going through the tournament process until the best one survives. So it's exactly that's right. Yeah. So basically each time here, look, we can see 100 generations, 10 generations. So it ran for 10 times, but within that an episode length is 200. So each one is 200 ticks of a market. So if we take it as a second, it's like 200 seconds, say, right? And then it's actually times 2, so it's 400. And we're saying that the elite size is, yeah. So now we have said, right, these are the best parameters. This is the best parameter we've found here, right? So we're now gonna we can now move to the dashboard, which has got the. I'll stop this. Hold on. Reloads. Right. So if we run this simulation here, we're running it on two systems. We're running it against the rule-based and the adaptive system. We can check which one performs better, right? And in different scenarios, they perform differently. So if we make it a simple system, so there's only 5 GPUs, and the arrival rate is only, say 3 per second, so 3 per step, 3 new jobs, right? Which could be random size. It could be quick jobs, long jobs, but also there's randomization added in terms of we can have spikes, we can have periods of rest where there's no network activity coming in, and it never sits idle. So when I'm saying here base rate 3, it could still be base rate 5. It's just the minimum base rate, so there's never going to be any less than 3 jobs coming in per step. Here I can also trigger a surge or trigger a shock to the market, which will happen during that simulation set. So for the minute, I'm just going to leave it bare. We're running simple number of GPUs, and we're running a base arrival rate of 3, and we're going to run it for 200 steps. So we just run that, and then I'll check the log while it's running. Right. So in this simple scenario where we're not really got much throughput, right, and there's not much throughput, and we don't also have a complicated GPU environment in the sense that there's only 5 GPUs. This is the results, right? So our system generates more revenue than the rule-based system, right? Even though on average the price on the rule-based system is set higher. The reason for this is because market death occurred here, right? And in our case, market death still occurred, but except we did it because we went 1 over the threshold. So six periods of non-arrival would be considered market death. We can see that we did actually generate more revenue than the other policy. Well, the GAs could be constantly training, like you say. It's just you have to use one GA at runtime, but each GA is basically being proposed by miners. It's kind of fitting into the block reward cycle. Like I can see that being a strong. This is it. It affects the market. That's the interesting thing. The price is so you can receive the stimulus from the market, and then you can affect the price, but the price itself affects the market, so it goes back in because the market will. That's where it really becomes this sort of kind of like. Yeah. So we can see here, even with a simplified system, which should theoretically allow the rule-based system to win, right, or at least come closer to being the better performer, where we don't have a complicated number of GPUs to load between, and we don't also have a high base level, and we don't have any kind of shock. But you can still see that the queue has spiked and then collapsed, spiked and collapsed, spiked and collapsed, right? There's no ability to try and manage that queue to actually keep the demand up and maximize the price, which has happened here. So you can see our resolution is higher, but we have actually tried to sort of keep it on our objective of 5, right? So we're near stable. It doesn't look particularly stable, but it's much more stable than this, which has just collapsed. Utilization, similarly, we just utilize it, a rule kicks in, we stop utilizing it. Oh, we utilize it, a rule kicks in, we stop utilizing it. Here, we've maximized and we're utilizing the GPU efficiently, right? Like 100%. Yeah, this is a simple case. I'm about to do a more complicated case in a minute, and that'll actually show how it really performs far, far better in that case. And then similarly here, you can see here the rewards basically dropped off and just shat itself, right? And the reason is the market died. So it tried to adjust the price, and you can see at step 8, step 9, step 10 already it was starting to fail. Whereas here, like if we look at step 10, we can see that we're at 9.2, right? So we're always achieving high rewards, and even when we drop off, we're dropping to 10 as our base. Like this market death occurred, it's getting nothing. And that makes sense. We only went 1 over in this threshold to be considered market death because I've set it at 6. Right, so if you kill the market enough that 6 cycles come in with no further traffic, you've basically killed the market. So let's up the CPUs to 11, and then also put this up to 11 as well. So now we have high numbers of traffic coming in, and we have a lot of GPUs to try and manage the jobs across. So I'll not inject any additional noise yet, no spikes or that, but I'll run this one. And this should allow us to not have market death, but also see again that we're outperforming the rule-based system. This is the first time I've used this library called Steamlit as well. It's like it saves you having to write any like any HTTP, any JavaScript or any CSS or any HTML. But it's not very good, so I'll probably just go back to just what I did before, which was stealing other people's front end, getting AI to generate me a front end, whereas now, like this is an actual tool for data engineers, but it's not great. So our GA in this complex system outperforms by 0.6 per step, 1.18x. The normal rule-based policy collapsed completely, and it had 24 consecutive steps with market death. There was no market death occurred for us. Difference in revenue 634, total revenue 805. So we generated more revenue. This here is actually wrong because what that's doing is taking it for the last step, which is not what we need, right? And same way CPU usage, that's actually the last step. This is average, so that's fine. I just need to fix this, right? Because that's why that looks off. You would say, well, why is that reward minus 2.1? They're correct. The only reason that reward's wrong is because it's the last step of that 200 cycle it went through, and it was that bad. It was at minus 241. Right, so let's add a shock. So let's add a surge first. So this is basically going to say we've got this base rate which is already fluctuating, but now we're going to add in some random massive spikes to see how the network reacts there. What I'll do as well, I'll let you ask questions and we can play around, but I should also train the model on a 0 generations just to show you a poor score, right? Interesting, like can be sometimes good or poor depending on what random values it ends up on, right? But it's literally random in the first generation, so you've got no real control. But sometimes that you could notice a score comes out at 130, sometimes it'll be minus 50, just depends. So again, with the same outperforming, right? And then this will be more interesting to look at on the graphs, I guess, right? So our Q, we maintained a QA. Well, at our last step, our Q was 4, right? And our total reward on the last step was 176. But the total revenue we generated, which is a relationship to that reward, is 807. So we've outperformed the additional model. Again, its last step was utilizing 40% of CPU. We were probably capped at 100 the whole way. Price, right? Resolution, 0.6. Our resolution here is 5. So the price has spiked up and then it's kind of dropped down, and we're looking at probably averaging out in the 2s. We've kind of came up, spiked down, managed to maybe sustain the price for a bit longer, and then overall we're kind of just sort of teetering above and probably going to nearly 0.3, and that's how we've accumulated more over time. The Q here has done exactly what the rule-based system always does, which is basically we have a queue, we process it, and then it collapses, and then we're then trying to react to try and salvage the market. And you can see there's like a tiny attempt, but overall 0 has came in, and that's why no money was generated. We are spiking and coming down, but we're reacting and kind of going back into an area that is considered like at least semi-balanced. And then the utilization, you can see again, maximum utilization, right back down to almost nothing, back up to nearly maximum, back down. Ours is initial problem that might have been the spike, right, the surge, but we've actually started to balance it out. Wait times, they're slightly reduced, right? Kind of a similar pattern, but they're reduced because the resolution's 20 here, resolution's 15 here. Big one, the rewards just drop off and completely shatter brick.